So I guess I'll get started. So the chapter 21 homework is due on Friday the 7th. That's Friday next week. The chapter 21 quiz is also on Friday the 7th. We will be finishing chapter 21 today. That first lab report that you did, if you didn't already turn it in, is due next week on Tuesday, when we'll have our second lab. Names?
Yeah,
So let's continue to talk about the crust. Name?
I'm sorry?
Your name.
John Agee.
Name?
And
So along when we have two plates running into each other, you can get tremendous forces that can lead to the buckling, fracturing, or shifting of big units of rock. This is one of the ways the mountains were named. And these forces can rupture the plate edges into huge displaced blocks and can eventually result in the formation of mountain ranges. So when you have two things coming together, you can get folding and faulting that leads to the formation of mountain ranges. Especially if you have two continental plates coming together, neither one of them can sink, so they have to bend and crunch and pile up. And the two basic forms of structural deformation, two basic common forms of structural deformation are folding, where the crust bends and folds, like if you take a piece of paper and you push the ends together, it folds or bends. Name? And faulting, where along cracks, it moves and slides up. So folding is when the rock layers buckle. They buckle into arches, folding up. Those are called anticlines. And when it bends down and forms a trowel, that's called a syncline. These are just the technical terms for the folds. And the folding happens when slow compressive forces apply extreme pressures on the rock layers, and it particularly occurs when the rock layers are under pressure from stuff above. So folding tends to happen more often deeper underground, where the confining pressure helps prevent faulting. The forces that cause folding can be exerted either horizontally or vertically. And in general, folding occurs mainly during the early stages of mountain building. Rock is going to fold before it breaks. It bends before it breaks. But yeah, folding occurs when the forces are relatively slow. When things are warmer, it tends to occur more deeper. And in an extensively folded area, it's a particular rock layer's resistance to erosion that determines what kind of topographic features occur at the surface. Yes.
Okay, perfect.
So that means that anticlines don't always form high ridges, because it's how things erode at the surface that determines the structure you get at the surface. Sometimes what you'll have is you'll have an anticline coming up, but because there were softer layers exposed by that, they get eroded down. So you might have a dip in the ground at the point of a rise in an anticline. And you can have the opposite happen. You can have a high spot at a trough because there's some material here that's hard to erode. So anticlines don't always form high ridges. It's how things erode at the surface that determines the structure of the surface. You actually have to look at the folds of the rock themselves. The case that you're most likely to see these is in road cuts. When they cut through a hill for a road, you can really see the rock layers there. Now, a fault is the other way that rock can handle compressive forces. So this is a fracture in the rock along which there has been visible movement of the two sides relative to each other. The rock, internal rock can either fold, bend and fold, or it can crack and slide along the crack and pile up on top of each other. So the stresses that form faults, there's basically three possibilities. You can have compressional faults when both sides are being pushed together and one side will slide up on top of the other. If the compression is vertical, you get uplifts. If the compression is horizontal, the crust gets shortened and one side slides up on top of the other. And you have tensional faults that are pulling apart. This causes the crust to lengthen. You have one side sliding down the other, stretching the crust out. And you can also have faults that slide side to side, transform, or they're also called strike slip faults. So faults, most of the terminology for faults comes from mining, because lots of very good places to mine concentrated minerals are along faults. Because what you have is that along the fault, minerals get deposited by liquid or various active fluids flow along the fault and can deposit concentrated minerals that are better for mining. It depends what you're looking for, but things for like gold and things like that, they tend to be concentrated in when people talk like a vein of ore, that's usually running along a fault line, like along a fault. So the terminology all comes from mining. Miners were the people who dealt with faults. So the crack between the two pieces of rock is the fault plane. It's the approximately flat planar surface along which the actual movement takes place. And then the two sides of the fault are called the hanging wall and the footwall. That's because when you make a mine, one of them ends up on top, the other ends up on bottom. Amen? One of them ends, so, because the fault plane is rarely perfectly vertical, it's usually at some angle. The hanging wall is the fault plane that's on the top of the fault plane. The footwall is the one that's on the bottom. Because when you make a mine running along the fault plane, the hanging wall is where you hang stuff, and the footwall is where you stand. Okay? So this all comes from mining. And then one side is going to move up relative to the other, depending on how the fault moves. The one that moves up relative to the other, if the fault is moving up and down. I mean, it could be just sliding side to side, but that's called the upthrown side. And that's not necessarily going to be the hanging wall. It could be the hanging wall or the footwall gets upthrown. Either one could go up. And there are three basic types of faults. There are normal faults, reverse faults, and strike slip or transform faults. Normal faults are faults where they're caused by tension. They're caused by pulling apart. This is where the hanging wall, the uppermost side, slides down the fault. It moves down with respect to the footwall wall. This is caused by things pulling apart. The crust lengthens at a normal fault. This is caused by tensional forces. Reverse faults are the opposite. These are when the footwall moves down with respect to the hanging wall, when the hanging wall is pushed up over the footwall. These are caused by compressive forces. The crust shortens. If you have two wedges in a normal, so if this was the fault, in a normal fault, this, my left hand here is the hanging wall, it would slide down and my hands would move apart. In a reverse fault, it would slide up and my hands would move closer to each other. And then lastly, a strike slip or transform fault is where the movement is side to side. Either side moves up or down. So here are some images. So here we have a fault. The footwall is side A on the left here. The hanging wall is side B on the right here. The fault plane is the plane in between them. If the hanging wall slides down, that is a normal fault. And you get a fault start. Looks like that. Here, if the hanging wall slides up, because the two sides are squeezed together, this is a reverse fault. And a particular type of reverse fault, where the fault plane is at a very shallow angle, is called a thrust fault. And then this is a transform or a strike slip fault, where the hanging wall and footwall don't move up or down, they just move side to side. So a thrust fault is just a particular type of reverse fault where the angle is particularly shallow. It leads to some extreme overlayering of stuff. You can get certain things. It has thrust faults just happen to create certain unique structures where you can end up with older stone on top of younger stone. And also, for really big thrust faults, they can create those massive earthquakes. We talked about the mega thrusts. So here is a short video about faults and the types of faults.
Hello everyone, this is Earth Science teacher Tim Martin, and in this video I want to introduce you to the geologic concepts of folding and faulting. When we look for faults and folds in the Earth, what we're really doing is looking for past evidence of plate tectonic motion. Let's take a minute to review the basic motions of plate tectonics. The first of the three motions is divergent motion. This occurs when magma comes up from deep within the Earth. This typically happens in the middle of the ocean. It generates earthquakes as the plates move apart from each other. This may also happen on continental plates as well. The next type of motion, convergent motion, happens when plates collide. Here we can see an oceanic plate subducting beneath a continental plate. As the plate subducts, it cracks and breaks, generating earthquakes. Finally, we have transform motion. This occurs where two plates slide or grind past each other. Again, this generates earthquakes. Now let's take a look at the structures identified with each of these three types of motion. To start off with, let's talk about rifts or cracks. When the Earth is pulling apart or forces are acting on it in opposite directions, the crust will thin, stretch, and possibly crack. These cracks are often known as rifts. This is caused by tension or divergent motion. A normal fault also happens with tension or divergent motion. If the rock is more rigid and less likely to stretch, it may simply crack, and when it does, one block may drop lower than the other. This is what's called a normal fault. Opposite the normal fault, we have a thrust or reverse fault. This occurs from compression or convergent motion. When two plates are pushing against each other, one plate may go down or another one may go up. This creates a thrust or reverse fault. Finally, a transform fault, or a strike-slip fault, occurs with lateral stress. When two parts of the Earth's surface are moving in opposite direction with respect to each other, one may slide, causing a transform or a strike-slip offset. While sometimes rocks break with faults, sometimes they're soft enough to fold. A fold occurs with compression or convergent motion. Sometimes rock layers may fold with an upward bend, Other times they may form with a downward bend. Both types of folds occur with compression or convergent motion. An upfold is referred to as an anticline. The downward or U-shaped fold is referred to as a syncline. Let's take a look at what this looks like with real geology. Can you identify the motion from these real images? Let's take a look at these 5 different features. Thingvellir National Park in Iceland is one of the classic locations where the Earth is splitting apart. On the right-hand side of the picture, we see the North American plate. On the left side, the European plate. As the plates are splitting apart, this rift or gap is opening up. This occurred through divergent motion. This picture of the Hayward Fault was taken in Fremont, California, in Central Park. You can see when the road planners built this road, they didn't intentionally offset the sidewalk and curbing. What happened here is part of the road was built on the North American plate, and the other part of the road was built on the Pacific plate. Here's the fault line, and we can see the further section is moving northward, where the side that the photographer is standing on is moving towards the south. Moab Fault is a dramatic fault that was revealed in a road cut just outside of Arches National Park in Utah. Here we can see several very large faults. As we identify the previously aligned layers, we can see that this brown stripe used to all be the same layer, but now has been offset with several normal faults. This represents divergent motion or tension. Browns Canyon of the Arkansas River goes through Salida, Colorado. Here we can see rock layers that have been folded. This must have occurred through compression or convergent motion. It's impossible to make a fold by pulling. Going from a large scale to a rather small scale, in Mosaic Canyon in Death Valley National Park, California, we can see this small layer was offset. The fault indicated in red, and these yellow layers are offset with a little bit of overlap. This indicates that this was a reverse fault caused from compression or convergent motion. So let's take a little quiz. Can you identify the motion in these next 5 images? Feel free to pause the video between each image. Number 1 is Katobe Knob, located in the Cedar Mountain Recreation Area in the San Rafael Swell in Utah. Number 2 is a rock structure that I found at Noosa Heads in Queensland, Australia. Number 3, a road cut near Orderville, Utah. Number 4, rock layers west of Wild Rose Campground on Wild Rose Road in Death Valley National Park. Number 5 is specifically called Earthquake Fault, located just outside Mammoth Mountain Ski Area in Mammoth Lakes, California. So, could you identify all 5 of these images? What sort of plate motion caused each? Are they normal faults, reverse faults, folds, or rifts? Let's take a look at each. Number 1, Katobe Knob in the San Rafael Swell in Utah. First, we identify the fault plane, located here. Then we identify the layers that used to line up, here and here. So we can see, because of the overlap, this must have formed from compression or convergent motion. Number 2, Noosa Heads in Australia. Again, the first thing to do is identify the fault plane, located here. Then the layers that as they used to match up, here and here. Because of the lateral offset, we understand this must have been transform or a strike-slip fault. Number 3, again, this is a road cut in Orderville, Utah. Let's identify the fault plane, leaning from left to right across the image. See the double brown lines towards the bottom of the image? These used to match up with each other. Thus, this is a normal fault, formed through tension or divergent motion. Number 4, along Wild Rose Road in Death Valley National Park. We can obviously see folds. These folds must have formed from compression or convergent motion. Finally, number 5, the earthquake fault near Mammoth Lakes, California. Again, this is a great example of a rift where the earth was experiencing tension and cracked open, causing this split in the rocks. Would you like a little more practice identifying folds and faults? You can download a slideshow of images that I've taken from around the world of places where we can see convergent, divergent, and transform plate motion.
So, let's talk about how mountains get built. So mountain building, the process of building mountains, occurs most often along and because of converging plate boundaries. The ways that mountains form generally involve plates coming together. So mountains can be classified into three broad categories based on their characteristic features. You can have volcanic mountains, you can have fault block mountains, you can have fold mountains. Volcanic mountains are mountains formed through a series of volcanic eruptions. Most volcanic mountains are located at convergent boundaries where one plate subducts, melts, and releases magma that forms volcanoes. So this is where most volcanoes occur. So along an oceanic convergent boundary, you get chains of volcanic islands like Japan, the Marianas Islands, the Aleutian Islands, lots of these volcanic island chains. The Aleutians, Japan, the Lesser Antilles, these are all examples of volcanic mountains. And they form on the plate that overlies the subduction zone. So this, you get volcanic islands when you have a plate melting underneath another oceanic plate. You can also get volcanic mountains along continental oceanic convergent boundaries. This generates things like the Cascades up in the Pacific Northwest, or the Andes along the west coast of South America. The continental plate always overlies the subduction zone, so the volcanic mountains form on the continental plate. So the Andes Mountains of South America were formed as the oceanic Nazca plate gets subducted between the continental South American plate. The Cascade Mountains, including, probably one of the more famous volcanoes in the US, Mount St. Helens, were formed as the small plate, whose name I cannot recall, up there, subducts under North America. And so what's happening is these oceanic plates are subducting, they're melting, they're releasing magma that rises up, and that forms the mountains. So here are the Cascades in Washington. Yeah, the magma is rising up from beneath. That's generally the case for all volcanoes. These are actual volcanoes. You can also get part of it where the magma never actually makes it to the surface. So you can get these big underground structures in them. Those are a little more common in continental, but you do get volcanoes along. So like Mount St. Helens is a volcano, it exploded. And there's a bunch of volcanoes all along throughout the Andes. But there's also magma that never makes it to the surface. Yeah. So that the whole process in more detail, there's a type of mountain building called Andean mountain building, where you get this melted plate, you get magma rising up, you get both volcanoes and structures that formed under the surface but never made it to the surface, never exposed to air. So the Sierra Nevada mountains in California were formed primarily of that sort of big magma structure underground that got lifted up and revealed. We'll talk about that when we talk about types of rock. Those are called plutons or bathos. Yeah. Now, you can also get mountains by fault processes, where you can get tilting and uplift of large crustal blocks. So basically, you can get huge blocks are cracked, lifted up, and tilt over and form mountains. So you get these fault block mountains that rise abruptly above the surrounding lowlands. This can be actually caused by normal faulting. So the Grand Tetons of Wyoming, so part of the Sierra Nevadas was lifted up through this process. Yeah, the Sierra Nevada mountains of California. It must have been misremembered. There are some mountains in the US that are these massive underground magma things. I don't remember which are which. The Sierra Nevada mountains of California and the Wasatch Range of Utah are all example of fault block mountains. So you can both get areas that are just like raised up, and then you can get areas that formed with lots of volcanoes. Yeah. Here's Mount Whitney, as an example of that. You can see how it's a very steep, sudden rise above the surrounding area. And then fold mountains are characterized by prolific folding of the rock strata. This is when two continental plates come together, they buckle and fold. There's also faulting involved in this kind of process. So examples of these are the Alps, the Himalayas, the Appalachians. These are places where the crust was compressed, folded, and piled up. You also tend to have large quantities of marine sediment on the top of these mountains, because they're usually caused by two continents running into each other, and that process basically scrapes everything off the bottom of the seafloor in the process and piles it up, and then that area is what gets pushed up to the top of the mountains. So this sedimentary strata was originally deposited below sea level, then it gets uplifted and incorporated into the fold mountains. So the top of the highest mountains in the world, the Himalayas, you can find marine fossils. So marine fossils are regularly found high in fold mountain ranges. I'm not sure if they're so common in the Appalachians because the Appalachians are a very old mountain range, so they've lost a lot of their upper layers. They're heavily eroded. But it is the case of the Himalayas. Like the top of a lot of Himalayan mountains are marine strata. Like you find marine fossils like that. Here are some fold mountains in Alberta, Canada. You can see that sort of folded structure here. The Himalayas are the youngest mountain range. So it's been formed via this process. So during the breakup of Pangaea, the subcontinent of India broke away from Africa, and as the Indian plate moved north towards Asia, the oceanic lithosphere was continually subducted below Eurasia, and basically the top layer of sediment kind of got scraped off. And during the time of continental collision, sediments were deposited in the marine waters between India and Eurasia, and that sediment got captured and piled up and pushed up during the collision. And the Indian subcontinent only actually impacted with Asia relatively recently, only a few tens of millions of years ago. And that is the process by which those mountains formed. So they're the youngest mountains on Earth. So that sedimentary strata that was deposited between Eurasia and India eventually got lifted up and folded into the mountains. And when the continental crust portions finally collided, the process of subduction was significantly slowed because suddenly you had two big, thick lumps of material that couldn't sink anymore. And so then even though that process wanted to keep moving forward, well, the only way it could move forward was by bending and piling up the material in the middle. And the edge of the Eurasian plate got lifted up, leading to the Tibetan Plateau. As the continental Indian plate was wedged underneath it, and the Indian plate continues to move north today, leading to the Himalayas actually getting higher. The formation of the Himalayas, the Indian plate was over here, the Eurasian plate is over here, the descending ocean plate is here, and material that had built up in between basically got scraped off and piled up on top. And this oceanic crust was subducted between Asia until the continental crusts collided, and the collision of the Eurasian and Indian continental plate led to the Himalayas. And again, the Indian plate is still moving north today into Asia, rising up that portion. The Himalayas and the Tibetan Plateau are both getting higher. That is the end of chapter 21. So I'll go over the review of chapter 21 and then I'll get started on chapter 22 so we can get a little ahead of schedule. So the two types of seismic waves are body waves that travel through the structure of the underground, and surface waves, which travel only on the surface. Surface waves are responsible for most of the damage caused by earthquakes because they move the surface more than body waves, so they cause more damage. The two types of body waves are more useful scientifically because they pass through the earth. The two types of body waves are P waves or pressure waves, which are compressional, and the movement of the rock is in the same direction as the movement of the wave, like sound, and S waves or shear waves, where the movement of the rock is side to side compared to the movement of the wave, like, I don't know, a wave on a string. And all body waves can travel through solids, both S waves and P waves. So they're also called primary and secondary for P and S. But only P waves can travel through liquids. Because when a shear wave, a secondary wave hits a liquid, it just slides and the liquid doesn't move because liquids can flow. So there's no shear forces don't travel through liquids. And P waves are faster than S waves. And by looking at the difference in arrival time between P and S waves, you can figure out how far away the center of the earthquake was. This is very similar to how, by comparing the time between the flash of light from lightning and the time the sound takes to reach you, you can figure out the time the thunder takes to reach you, you can figure out how far away a bolt of lightning is. The same idea, two different waves that travel at different speeds. It's a little easier to think about with lightning because the difference in speeds is much, much greater because light travels much, 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 much faster than sound, but it's a similar process. P waves are faster than S waves, so the difference in speed lets you figure out how far away you are. The velocity of body waves depends mainly on the density of the material they pass through. In general, I believe they move faster in denser materials. The four layers of the earth from the surface to the interior are from the surface, the crust, the mantle, the outer core, and the inner core. Those are the layers based on material property. All the layers are solid except for the outer core, which is liquid. Continental crust is thicker than oceanic crust. It's also less dense. Continental crust is mainly composed of granitic rock, rock that's like granite. Oceanic crust is mainly composed of rock that's like basalt, the basaltic rock material. The boundary between the crust and the upper mantle is called the Mohorovic discontinuity, or MOHO. The solid, rigid layer of the crust and upper mantle we call the lithosphere, rock sphere. Litho means rock. The layer that lies below the bottom of the crust that makes up the upper mantle that things can slide around on, that's the asthenosphere. The movement of the continents over time from one large supercontinent to their present positions is referred to as the theory of continental drift. The name of the supercontinent that broke up around 200 million years ago is Pangaea. It's not the only supercontinent that's ever happened. There have been several before that. The name of the scientist who proposed continental drift theory was Alfred Wegener. And his evidence, the three areas of evidence, were biological and paleontological, geological evidence of magic rock types, and like the fit of the continents, how the continents fit together. There was also some glacial evidence in there. And the theory of continental drift was not generally accepted by the scientific community because he didn't have a mechanism for continental drift. He had no way of explaining how the continents moved, just that they have. He just stated that they have. So that was the problem. And his description of like continents crashing through oceanic crust didn't really make sense. The name of the geologist in the 1960s that used ocean floor soundings to propose the theory of seafloor spreading was Harry Hess. What happened to the magnetic field of the Earth several times in the past, that's recorded in the rock material bordering the Mid-Atlantic Ridge, is that the magnetic field has reversed several times in the past. And that's recorded in the magnetic fields of the rocks, because the rock get magnetized in the direction of the magnetic field when they cool. And then when the magnetic field reverses, they get magnetized in the opposite direction, and you can measure that difference. And the theory of continental drift and seafloor spreading have now been combined into the single theory of plate tectonics. Continental crust is generally older than oceanic crust, because oceanic crust is the crust that is created and destroyed. Continental crust sticks around. So like some of the crust in up in Canada is 3-4 billion years old. There are some very, very early rocks found up in Canada, while most oceanic crust is less than 200 million years old. Because again, oceanic crust is what gets created and destroyed. Continental crust sticks around. So about how many plates are thought to exist? Around 20. With 8-ish big ones. And most volcanic and earthquake activity occurs along the boundaries between plates. The three types of plate boundaries are convergent, where plates are coming together, divergent, where plates are spreading apart, and transform, where plates are sliding side by side. The layer that the Earth's crust rides on is the asthenosphere. Plate movement is believed to be caused by convection currents in the Earth's upper mantle. Like when you boil water, the water cycles around. That process is happening within the Earth's mantle as you heat up the hot, parts of the mantle are hotter than others. So warm magma rises, travels along sideways, then sinks as it cools, and that creates a big current. The same thing happens, in rooms with air and such. Two plates moving apart is referred to as a divergent boundary. And at the boundary described in a divergent boundary, the youngest rock is found nearest to the boundary, because that's where new rock is forming. Further away from the boundary, the rock gets older. Two plates moving towards each other is referred to as a convergent boundary. The three types or combinations of plates moving towards each other are the oceanic-oceanic convergence, where two oceanic plates converge. Oceanic continental convergence, where an oceanic and a continental plate converge, and a continental convergence, where two continental plates converge. And the one that doesn't show much subduction is the continental convergence. Because in general, for subduction to occur, you need the thinner, denser oceanic plate to sink. So when two oceanic plates come together, one of them will sink. When oceanic plate meets a continental plate, the oceanic plate will sink under the continental plate. But when two continental plates meet each other, they're too light and thick for either one to sink, so they just pile up. The type of crust that always subducts is oceanic crust. Deep sea trenches usually form during oceanic and oceanic continental convergences, where one plate subducts, you get a deep sea trench. The combination of plate movement that results in very high mountain ranges, such as the Alps, is continental convergence. This is, again, what causes the Himalayas and the Alps, where two continents slam together and pile up. And the type of plate boundary that involves plates moving past each other is a transform plate boundary, like at the San Andreas Fault. Most volcanoes form at, most volcanoes that you'll see at the surface are going to be at convergent plate boundaries. You also get lots of volcanoes at divergent plate boundaries, but they also tend to be underwater, so they're less obvious. Because eventually, I mean, you do get them at the crust at divergent plate boundaries, but eventually that crust tears apart and the area floods, and they end up underwater. But, you know, most famous volcanoes are at convergent plate boundaries. Most earthquakes form because of the movement of tectonic plates. A fracture in rock that's caused by visible movement of said plates is called a fault. The longest fault systems are usually at transform boundaries, the side-to-side ones. The actual point in the Earth's interior where an earthquake originates is called the focus. The point on the Earth's surface directly above the focus, where the earthquake hits the surface first, is called the epicenter. The device that's used to detect and measure earthquake waves is called a seismograph. The earthquake scale that measures earthquakes by the energy they release is the Richter scale. The earthquake scale that measures earthquake by the damage they cause is the Mercalli scale, the modified Mercalli scale. An earthquake on the ocean floor can produce giant waves called tsunamis. There are a few other ways you can get tsunamis, but the most common is an earthquake on the ocean floor. Massive landslides can cause them. Volcanic eruptions, things like that. Actually, there was a really interesting one that happened that was caused by a landslide recently. It was a tsunami in like a bay, and the bay was just right, and for the tsunami to basically bounce back and forth at resonance in that bay. And they recorded this continuing for weeks. It was like more than a week. It was like 9 days or something. More than, yeah. It was just the right shape and size to keep this wave continually fed, bouncing back and forth. But yeah, it was a glacier collapsing into the water that triggered it. So it was basically a landslide. An earthquake, yeah. Mountains are usually formed when the crust is deformed through folding and faulting. Arch-shaped folds that go up are called anticlines. So arch and anticline. And trough-shaped folds that go down are called synclines. The kind of fault that forms when two sides of a rock formation are pulled apart is a normal fault. So normal faults come from stretching or tension. The kind of fault that forms when two sides of a rock formation are pushed together is a reverse fault. And the kind of fault that forms when two rock structures slide by each other is a transform or strike slip fault. And besides being formed from faulting and folding, mountains can also form from volcanic processes. So that was chapter 21. We definitely still have some time. So let me pull up chapter 22. And there we go. So here we're going to talk about minerals, rocks, and volcanoes. So we talked about sort of the big picture. Let's look at the stuff that, the Earth's crust is made out of. We will define the characteristics of minerals. We'll talk about what a mineral is, how we can define what is a mineral and what's not. We'll talk about the formation of minerals from magma and other solutions. We'll describe the physical and chemical tests that can be used to identify minerals. We'll go over how to use crystal form, luster, hardness, cleavage and fracture, streak, special properties, texture, density and specific gravity, and density and specific gravity to identify various minerals. How you can tell minerals apart. We'll describe and give examples of common mineral groups, including the silicates, carbonates, and oxides. Those are some of the more common mineral groups. We'll talk about the usefulness of various minerals, including ores and gems. We'll go over what types of minerals various gems are as well, at least some of them. We'll talk about the various processes involved in the rock cycle and discuss the conservation of matter during the formation, weathering, sedimentation, and reformation of rock materials. We'll describe how the composition of magma influences the formation of igneous rocks. We'll talk about the factors that influence how igneous rocks melt and crystallize. We'll look at the different types of igneous rocks in terms of mineral composition and texture. We'll describe the relationship between magma cooling rates and grain size. We'll talk about volcanoes, shield, cinder cone, and composite volcanoes in terms of their formation and the type of eruption they have. We'll look at the types of magma found in volcanoes and how magma type influences volcanic eruptions. We'll look at the role of pressure in dissolved gases in volcanic eruptions. We'll look at the types of material expelled during a volcanic eruption. We'll describe the processes involved in the formation of sedimentary rocks. We'll look at the main structural features of sedimentary rocks and how these features can provide clues for the past life on Earth. We'll look at the formation of clastic or inorganic sedimentary rocks in terms of grain size. We'll look at the formation of chemical and biochemical sedimentary rocks. We'll look at the various types of metamorphism involved in the formation of metamorphic rocks. And we'll describe the characteristics of foliated and non-foliated metamorphic rocks. So in this chapter, we're going to look at rocks and minerals. Rocks are made of minerals in general. Technically, they're made of minerals and mineraloids, because there's a few things we'd like to consider rocks that are not technically minerals, but we'd like to include them as well, because everyday people would consider them rocks. But we'll consider rocks and minerals. We'll see that specific rocks and minerals form in response to a myriad of Earth processes. Therefore, existing rocks and minerals can tell us about past geologic events. We understand how rocks and minerals form. We know that when we find these rocks and minerals, they had to form through that process, so that tells us what was happening in the past. So, a mineral. A mineral is a naturally occurring, inorganic, crystalline solid substance that consists of one or more chemical elements in fairly specific proportions with a distinctive set of physical properties. So the things that cause something to not be a mineral, if it's not naturally occurring, it's not a mineral. If you made it in a lab, it's not a mineral. That one's sort of fun because you can make two identical, you can have a naturally occurring thing that's identical to an artificially made thing. One's a mineral and one's not. That's a little weird, but that's just, yeah. Inorganic, it has to not come from a living thing. So stuff that came from living things, not a mineral. So for example, naturally occurring, cubic zirconia. If you have like a cubic zirconium ring, those are made in a lab. Those are artificial. There are artificial gems out there. Those are not technically minerals. Inorganic, something like amber. Amber is not a mineral because it's solidified tree sap, hardened tree sap. It comes from a living thing. This line can get a little fuzzy, but generally, when we talk about that, mostly we mean it's not from a living thing. We'll get into a little bit of fuzziness. And then crystalline. Amber is also not a mineral because it's not crystalline, but a crystalline solid, it means that it has something that has a repeating internal structure to its atoms and molecules. So glass is not, you can have naturally occurring inorganic glass like obsidian. Obsidian is not a mineral because it's not crystalline. Its internal structure is random. That's what it means to be a glass. So minerals are around us everywhere. Some are very valuable, things like diamonds, sapphires, and emeralds. While other minerals are very common, calcite, quartz. Well, you can get sapphire for pretty cheap, but it's artificial. And you can get the same mineral that makes up sapphires and rubies for dirt cheap, but you'd never use it as a fancy gemstone. If you've ever used an emery board, emery is the same mineral that makes up sapphires and rubies. Same thing, just it's a totally unattractive, tiny fine dust in it. So other minerals are very common, things like calcite, quartz. These are super common. Calcite makes up limestone. Mineralogy is the study of minerals. And we can talk about different various rock types or ores being rich in particular minerals. So iron ore, gold ore, or copper ore are rocks with minerals in them that contain lots of iron, gold, or copper. Gold ore, actually, the mineral that it contains is just gold. It's pure elemental gold. But iron ore and copper ore, if you have them, are usually various minerals that have lots of iron in them, like hematite or some other thing. They're more complicated. But copper has various copper minerals. And for something to be an ore, rocks classified as ores have a commercially viable amount of some type of element or mineral. So if you suddenly developed a new technique for extracting the element or mineral from some rock, it could change from just being regular rock to being an ore. So it has to be commercially viable. That's the definition for what makes it an ore. So whether or not something is an ore can change over time. So here are some rock forming minerals. Olivine is a particular mineral that's found very deep. I think it's also it's very similar to the mantle. This is plagioclase feldspar. This is halite. This is salt. Same thing as your table salt. But your table salt wouldn't be considered a mineral generally, because it was usually formed by a process that would be considered artificial. But like rock salt, that's how. There's pyroxene, there's amphibole, there's biotite, muscovite, these are both micas. There's samorphite, there's sodium feldspar, orthoclase feldspar, there's quartz. Glass and quartz are actually very similar. They're made of very similar material, but they have different properties. So you have a gypsum we use to make drywall, limonite, hematite, this is an iron ore, and calcite. Now, only 8 chemical elements make up the major constituents of most minerals. These are the most abundant elements in the Earth's crust. The 2 most abundant elements in the Earth's crust, these are actually in order of abundance, I believe. They are, the 2 most abundant are oxygen and silicon. So oxygen, silicon. Then after that, in much smaller, in significantly smaller amounts, we have aluminum, iron, calcium, sodium, potassium, and magnesium. Now, well over 2,000 minerals have been identified in the Earth's crust. I believe it's something like 5,000 now, but some of those are super rare. Like they only exist in one place on Earth. And some of them are dead common, but only about 20 of these are common. And less than 10 minerals account for more than 90% of the Earth's crust by mass. There's a handful of minerals that are super common and are everywhere. So the most common type of mineral is feldspars, and then quartz, I think, is next. I'm not 100% sure. So here are the elements. Oxygen, 47% of the crust is oxygen. Silicon, 27%. So oxygen and silicon consist of 74% of the elements by mass in the Earth's crust. They are by far the most common thing. Oxygen is by far the most common. The most common type of minerals involves silicon oxide, silicon and oxygen together. But most minerals that don't have silicon in them still have oxygen. That's why oxygen is by far the most common thing in the Earth's crust. Because oxygen is very reactive. And then we have like aluminum, iron, calcium, sodium, potassium, magnesium, and then everything else. 82 other elements. So most of the minerals that form crustal rocks have significant amounts of oxygen and silicon. This is the silicates. This is the biggest group of minerals. The mineral quartz is pure silicon dioxide, or silica. It's entirely composed of oxygen and silicon and has the chemical formula SiO2, silicon dioxide. For every silicon, there is 2 oxygens. What it is that every silicon is surrounded by 4 oxygens, but each oxygen shares with another silicon. So there's this sort of there's these sort of tetragonal structure, and they're all tied together. And silicates are the most abundant family of rock-forming minerals in the crust. So quartz and the many other minerals that contain oxygen and silicon are called silicates. And these are the most abundant minerals in the Earth's crust. So here are some examples of mineral. This is a short video about gems, minerals, crystals, and rocks, and what's the difference. The general difference between rocks and minerals is that rocks are made of minerals. So you can have a rock that's made of a single mineral, but your average rock is made of a mixture.
What are minerals, rocks, crystals, and gems? What's the difference? Well, to start off simply, rocks, crystals, and gems all can be made up of minerals. So what the heck is a mineral? A mineral is a solid made by the natural activities of Earth. like lava spewing out of volcanoes or water dripping down through cracks in caves. Fluorite, gold, and calcite are just a few mineral names you might recognize. Minerals are made up of elements that come together in a regular, specific pattern. These geometric groups of elements are the building blocks of a mineral. A crystal of that mineral forms when these building blocks stack on top of one another, repeating their arrangement to form a three-dimensional object with flat faces. Quartz, for example, has a crystal structure made of oxygen atoms and silicon atoms that repeat in a shape that looks like a rhombus. The shapes that these chemical building blocks take are different from mineral to mineral. Sometimes, two minerals can be made of the same elements, but with different building blocks making up their structure, like diamond and graphite. The large geometric shapes and flat faces we see in crystals reflect what happens when these building blocks repeat over and over again. Now let's move on to rocks. A rock is a solid object made up of mineral grains, but it can have many different minerals inside it, and you don't see the same repetitive shapes that you see in crystals. Granite is an easy example. You can see the different grains of many types of minerals making up a piece. Limestone is also a rock, even though it's usually made of mostly one mineral, calcite. But limestone is made of calcite fragments mashed all together, and a calcite crystal has order and a geometric shape. So where do gems fit in? They have a geometric shape, and many look like crystals, right? But really, gems are minerals or stones that have been cut, ground, and polished by people to enhance their beauty. A finished gem may look very different from the original mineral it was carved from. Many times, gems are shaped with different flat faces to catch and scatter light. They aren't always minerals either. They can be made of things that come from animals and plants, like pearls or amber, or they might even be man-made in a lab. Let's make like a crystal and repeat that one more time. Think about pyrite or fool's gold. Pyrite is a mineral made of iron and sulfur. Those elements come together in the shape of a cube and repeat to form a pyrite crystal. These crystals can get so big you can see them with your naked eye. Other times, the pyrite crystals are just flecks in a rock like slate. And if it was cut and polished with flat faces, it would be considered a pyrite gem. So there you have it, crystal clear. The difference between minerals, gems, rocks, and crystals.
So that was sort of the difference between those. So the silicate minerals are based off of a network of these tetrahedrons that consist of a silicon. So they're little pyramids with a silicon in the middle and an oxygen in each of the four corners. These are called the silicon-oxygen tetrahedra. Covalent bonding occurs within the tetrahedra. The silicon is covalently bonded to the various oxygens within the tetrahedra. And then those tetrahedra bond to each other in a variety of different ways. And there's a significant amount of variation in the structural arrangement of these tetrahedra. So you could have the same stuff arranged in different ways, can create different minerals. The classic example that people give is with carbon. Pure carbon can form naturally in a number of ways. One of these is in a fully interconnected crystal structure that's covalently bonded in all three dimensions. That forms diamond. But it can also form with a crystal structure where the carbon is bonded together in flat sheets that are layered on top of each other. And that forms graphite. And they have dramatically different physical properties. Diamond is super hard and tough. Well, it's super hard. It's clear. Graphite is black. It's soft. And it has very different properties. Diamond is the hardest mineral in existence. Graphite is one of the softer ones. We use it to write as a pencil. And we use it as a lubricant. Diamond we use as an abrasive. Graphite we use as a lubricant. Is sort of how opposite they're gonna be. They're made of the same stuff. So in theory, you can convert one into the other. It would be complicated and a pain in the butt, but it would be possible. So with silicon, the silicon oxide tetrahedra, they can connect in various different ways. And the different variations in how they connect and what is mixed in with them leads to different minerals. So the silicon oxygen tetrahedra can exist independently with no sharing of oxygen, or they can share oxygens in various ways. So the basic building block of the silicon mineral family is this tetrahedron with 4 oxygens and a silicon in the middle. And you can have this structure, the oxygens, this whole thing comes out negatively charged. So if these exist independently, there has to be some other positively charged ion in there to mix with them. This happens. But you can also share some of the oxygens, like in quartz. Quartz, all the oxygens get shared and it balances out. So, in addition to oxygen and silicon, most silicon minerals also contain aluminum and 1 or more other elements. So there's other stuff mixed in with these tetrahedrons. And the various silicon minerals result from the different structural arrangements of the silicon oxygen tetrahedron building blocks and the different metal ions that are within these structures. So they can be arranged independently, in single chains, in double chains, as continuous sheets, or as a 3-dimensional network. So you can have them, the tetrahedrons independently. They can be chained up like this with a bunch of these chains. You can have double chains like this, where 2 of these chains are bonded to each other. You could have flat sheets like this, or you can have a 3-dimensional network. The 3-dimensional network, if there's nothing in it, that's quartz. If there are other minerals incorporated in it, that's how you get feldspars. So the most common silicon minerals are the feldspars. These are a group of structurally related. They're all 3-dimensional network minerals that are the most abundant minerals in the Earth's crust. There's 2 basic types of feldspars. There's the plagioclase feldspars, which have oxygen, silicon, aluminum, and calcium or sodium, and the potassium feldspars, which have oxygen, silicon, aluminum, and potassium. And all silicates have silicon and oxygen in their formulas. The feldspars, it's a 3-dimensional network of the silicon oxygen tetrahedrons with these other ions in the gaps in between. So this is albite, which is a sodium-rich feldspar. This is anthrite, which is a calcium-rich feldspar. Here are some other silicate minerals. There's a feldspar. This is a 3-dimensional network. Quartz, also a 3-dimensional network, but with no other significant quantities of other elements in it. It's just silicon and oxygen. Though if you see quartz that is various colors, which may have various names like amethyst or so on, that is just tiny amounts of impurities that cause those colors. So for example, there's olivine. This is got lots of iron and magnesium in it, as well as silicates. There's mica. The micas form with sheets of the silicate tetrahedrons form sheets, which is why mica, you can peel off layers that form sheets. And this is pyroxene down here. They all contain silicon and oxygen along with other elements. So olivine contains like magnesium and iron. Now, so that's the silicates. That's the most common type of mineral. There are also non-silicate minerals. Non-silicate minerals comprise less than 10% of the minerals in the crust. And the three most common groups of these are the carbonates. These are minerals with carbonate ions in them, which is CO3, if I remember correctly. Oxides, minerals with oxygen ions in them. They're various metal oxides generally. And the sulfides with sulfur. There are also sulfates, which is another, that is like a sulfur and oxygen combination with other stuff. And then pure elements such as gold, silver, and some gemstones, diamond, ruby, and sapphire are also non-silicates. In fact, ruby and sapphire are technically oxides. Diamond is just pure carbon, so it's just a pure element. But ruby and sapphire are actually the same mineral. The difference in color has to do with differences in the impurities. So the mineral in question is called I want to get the name right, and I am blanking on it. So let me just quickly look this up. Corundum, that's it. So the mineral in question is called corundum. It's aluminum oxide. So it's aluminum and oxygen. That's the components of rubies and sapphires. And another corundum that is commonly used is emery. So if you've ever used an emery board to file nails, emery is, well, it's like a black corundum, and it generally forms without not making nice, pretty big crystals, but like more tiny crystalline structures. So it's easy to turn into a powder to use to file your nails and such. But yes, ruby, sapphire, those are differentiated based on nominally color. Basically, rubies are red, sapphires are most everything else color-wise. Is the more general one. And then there's emery, which is a specific one that's black. But they're all corundum, they're all the same thing. So like rubies are red because they have chromium, is a small impurity. Sapphires get their colors from other impurities. So carbonate minerals form when the carbonate ion, which is CO3 minus 2, bonds with various metal ions. So you can have calcium carbonate, magnesium carbonate, molybdenum carbonate, iron carbonate. Various metals can bond with the carbonate ion. The one you probably run into most often is calcium carbonate or calcite. That's what makes up limestone and also marble. So CaCO3, calcite, is a very common carbonate mineral. It readily reacts and dissolves in acidic water. So limestone, because of this, limestone deposits are where you get dramatic caves, because those areas can be hollowed out by underwater water flows, basically. And calcite's a very common mineral component of the rock limestone. And so limestone will dissolve over time in slightly acidic groundwater. This leads to cave formation. So most of most caves are formed from the limestone dissolving. Oxides and sulfides form through the bonding of oxygen ions with metallic ions. So, there are various iron oxides, Fe2O3, tin oxide, uranium oxide. These are all oxide ores for the respective metallic ion. The most common iron oxide you're going to run into is rust. That's an iron oxide, but there's several different iron oxides. Sulfide minerals form through the bonding of silicon ions with metallic ions. So iron, lead, copper, zinc, and others can bond with sulfur. Did I say silicon? I meant to say sulfur. It's sulfur. So iron sulfide is pyrite. That's commonly called fool's gold. copper iron sulfide, lead sulfide, which is Galena. Galena is a town in western Illinois that they mined a lot of lead in. It's named after the mineral you get the lead from. And zinc sulfide are all sulfide ores for the respective metallic ion. You may have heard of mercury sulfide is what you make vermilion from. So that's not actually a good thing to use around as a paint, as a color. It forms a red gem that I'm blanking on the name of again. Sorry for this. Right. Here's some sulfide. This is pyrite, which is iron sulfide. It's yellow and shiny like gold, but it is very much not gold. Here's uranium dioxide. This is the primary ore of uranium. It's actually also uranium dioxide is what they use in nuclear power plants. You don't actually need to make uranium metal to do for a nuclear power plant. So they actually leave it as a uranium oxide because it's actually easier to work with. And here's carbonates. This is calcite, the primary component of limestone. And I think I will stop there for now. So I'll see you all next week. We will have a lab on Tuesday. Yeah, have a nice day.